So we're Team 8 with ME461. Our project was to do DC generator modeling and control. The team members are Palmer Corbett, Brandon Mason, and Taylor Sun. So our project was to model a DC generator that supports households when main power is unavailable. The model is a DC generator as an assumption because we didn't want to model an AC generator. And we also downscaled the model from 120 volts to 10 volts due to lack of specification on 120 volt DC motors. The system requirements we chose were to limit overshoot under 2.5%, and we wanted to keep our rise time under 0.5 seconds so that way the response for when additional load is required is quick, and we wanted zero steady state error. This is the block diagram. So moving left to right, the PID controller is first, followed by the driving DC electric motor. We were initially considering a gasoline engine but replaced it with a DC electric motor as a simplification. Followed by that is the DC electric generator, which is the driven DC motor and has a feedback loop for torque, followed by the generator circuit dynamics, and then the voltmeter dynamics from the sensor feedback.
So for our controller, we decided to use a PID controller in order to limit overshoot, decrease rise time. We were able to tune the PID controller experimentally, both with a little bit of guess and check, and then using the Bode plots and the root locus. Here is our root locus plot. You can see some of our imaginary poles. And then our step response, you can see that there's a slight delay in the step response, and our overshoot is really small, and our rise time meets our specifications. So here's our Bode plots, and the open loop in blue actually has two gain margins because it actually crosses over 0 decibels twice, but the closed loop only has one gain margin, and MATLAB showed the closed loop system to be stable.
Now looking at the disturbance rejection, you'll notice in the step response that the disturbance step is actually amplified quite a bit, so we were unable to both reject disturbance and achieve our time domain specifications with the single controller. So this would be sort of a future work to try to meet specifications for both and try to balance between the two. And you can see here's our closed loop Nyquist plot. So the contour doesn't include -1, showing that the system is stable. So some takeaways from this project. For one, root locus tuning is quite a really powerful tool to trying to understand how to make your system meet its specifications. And particularly when you're working with PID tuning, which is very robust since you have 3 terms that you can just move around as you need. Furthermore, when you're working with these kinds of systems, it's important to make simplifications where you can and where it's appropriate because it makes modeling and controlling significantly easier. Thank you.